Recall that in previous chapters we were discussing things like ionization energy and electron affinity. And what ionization energy is it's the energy that's needed to put into a system in order to liberate an electron from an atom or from an ion. Now, electron affinity is kind of like the flip coin of that. It's the actual energy that is released, oftentimes released, when an electron is added to a species. So these are the electron affinities for chlorine and sodium. And if you notice, if you add these two together, which would be the appropriate way to calculate the amount of energy change, if you add them together, you would end up with a positive number. 495 is a positive number. Negative 349 is a negative number. And so when this occurs, that positive number means that we actually have to put energy into the system. It's a net positive difference between the two, and so we'd have to put energy into the system. And so when sodium chloride is formed, you would think that it would actually require energy to put into the system, whether in the form of heat or electricity. Some sort of energy has to go into the system. But in this case, we know actually that when this bonding occurs, it's actually an exothermic process. And what we mean by exothermic is that it releases heat. It releases energy in the form of heat. Well, if that's the case, there's got to be a third energy component that occurs when we get sodium and chlorine to form this ionic compound. So the question is, why is the reaction of sodium metal and chlorine gas, this question down here, to form sodium chloride so violently exothermic if the ionization energy and the electron affinity, the addition of those two together, will give you a positive number for the energy value? And so the answer to that comes in the form of lattice energy. Now, lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So what does that mean? Well, recall that sodium chloride is sodium ions and chlorine ions actually combined together. So this lattice energy is the amount of energy you have to put into the system in order to break these two into their ionic species, just chlorine ions floating in air and sodium ions floating in air. And the energy associated with this is shown here by Coulomb's law. So the energy associated with the actual lattice or crystal formation of this structure is given by this equation here. It's equal to some constant times the charge on one of the ionic species times the charge on the other ionic species over the distance between those two species. Now remember, in the previous chapter we were looking at ionic radii. And so the bigger the species is, so the bigger the individual species is, the bigger the distance between those two are, which would mean the lattice energy would go down. The larger the charges are on the individual ions, the lattice energy goes up. And so if you consider something with sodium ions and chlorine ions, it's got a +1 charge and a -1 charge, right? So sodium has a +1 charge and chlorine's got a -1 charge. If you consider something like magnesium chloride, all of a sudden we have a 2+ charge and a -1 charge. And so the attraction between magnesium and chlorine is greater. The lattice energy is greater because now we would have a 2 here and a 1 there. So 2 times 1 is twice as large as 1 times 1. Now the distance between the two, this is slightly larger than sodium. So magnesium is slightly smaller than sodium, isn't it? So it's actually slightly smaller than sodium. And so the distance between sodium and the chlorine atoms is actually shorter. So that distance is shorter. And so you would expect the crystal of magnesium chloride to actually have a stronger lattice energy, more energy required to break these two apart than to break these two apart.